Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the 7th lecture of Discrete Structure CSC 102. In the previous lecture, we were discussing predicates, set notation, universal and existential quantifiers and statements. We have also discussed how to translate between the formal and informal languages, that is from universal and existential statements to informal language, and from informal language to these notations of universal and existential quantifiers. We have also discussed universal conditional statements and what are the equivalence forms. We have also discussed implicit quantification and their negations. Today we are continuing this topic and we start predicates and quantified statements too. In today's lecture we discuss mainly the statements containing both universal and existential quantifier, and then nested quantifiers and the relationship between for all and there exists, that is universal and existential quantifiers. We shall also discuss universal instantiation statements, universal modus ponens and tollens, and we shall also discuss the converse and inverse of universal conditional statements, converse and inverse errors in universal modus ponens and universal modus tollens. Now, how to interpret multiply quantified statements, and in what situations these multiple quantified statements, that is for all and there exist, such type of quantifiers exist. For example, if in a college cafeteria line has 4 stations, salad, main courses means main dishes, or you can say principal dishes, desserts and beverages. The salad station offers a choice of green salad or fruit salad. The main course station, that is principal dishes or the main dishes station, offers spaghetti or fish. The dessert station offers pie or cake, and the beverage station offers milk, soda or coffee. And 3 students, Uta, Tim and Yuan, you can name any 3 students. For example, here they go through the line and make the following choices. The first student, Uta, he choose green salad, spaghetti, pie and milk. The second student, Tim, he chooses fruit salad, fish, pie, cake, milk and coffee. And the last student chooses spaghetti, fish, pie and soda. We can express all these choices in a figure with the help of figure. For example, this. So here we have options. The first station, salads. Second station is main courses or the principal dishes. Third station is for dessert, and the fourth station is beverages. Now these lines shows the choices of the students. For example, the first student, Uta, he selects greens from the salad station, he selects green salad. From the second station, main courses, he selects spaghetti. From the third station, desserts, he selects pie, and the fourth station he selects milk. So in the form of a figure or graph, we can represent all the choices of these 3 students in this form. Now we have to write each of the following statements informally and find its truth value. You can see that in these statements we have more than one quantifiers. For example, in the first statement we have existential quantifier here and the universal quantifier here. In part A, in this statement, we have to write it informally in a simple sentence form, and we have to calculate its truth value. So the first question is, or first statement is, there exists an item I such that for all students S chooses I. What does it mean? There is an item I, means from all of these items there is one special item such that all students chooses that item. In an informal language we can write it as, there is an item that was chosen by every student. So in an informal language we can write it like this: there is an item that was chosen by every student. So now from the figure, from this picture, we can see whether there is an item which is chosen by every student. Example, here green salad is being chosen by only Uta, fruit salad chosen by Tim, spaghetti is chosen by Uta, spaghetti is chosen by Yuan. Tim has not selected this item. Fish has been chosen by Tim, fish has been chosen by Yuan. So this is not that item which is chosen by everybody. Now here pie is chosen by Uta, pie is chosen by Tim, pie is chosen by Yuan. So pie is the item which is chosen by all these three students. So pie is an item which is chosen by every student. So we can say that this statement is true. There is an item which is chosen by every student. Every means all these three students. So this statement is true. This is true because every student choose pie. So every student means all these Uta, Tim and Yuan, all these three students selects pie. So this statement is true. Its truth value is true. Now we come to the second statement B. There exists a student S such that for all items I, S chooses I. Now what does it mean? Informally, there is a student, there is at least one student such that for all items I, S choose I, means there is a student who chooses every item. So here with the help of this figure we can see that there is no student who chooses every item. So this statement can be written informally: there is a student who chooses every available item. This is false because no such student among these three students chooses all these items which are available in four stations of these salads, main courses, dessert and beverages. So there is a student S such that for all items I, S chooses I. This statement is false because there is no student who selects all these items. So the second statement is false. Now come to the third statement, C. In C statement, what is this? There is a student S such that for all stations Z, there is an item I in Z such that S chooses I. This means that there is at least one student S, and in all stations there is an item I in Z such that S chooses I. Means there is a student who chooses at least one item from every station. So this is I think this is true. So there is in the informal language, this statement, the C statement, can be written as: there is a student who chooses at least one item from every station. That is what I have explained you earlier. So this is a true statement because all these three students have chosen at least one item from every station. That is, Uta, he chooses green salad from first station, salads. From the second station, main courses, he chooses spaghetti. From third station, he chooses pie. From fourth station, he chooses milk. So from every station, he chooses at least one item. So the statement C, there is a student S such that for all stations Z there is an item I in Z such that S chooses I. So this statement is true. All the other two students have also chosen at least one item from each main station. Now come to the last statement, which is D. For all students S and for all stations Z, there is an item I in Z such that S chooses I. This is what we have discussed in part C, but here we have changed only here. So we have to check whether every student has chosen at least one item from every station or not. Here the first student here, which is Uta, he has chosen from first station green salad, from second station spaghetti, from third station pie, from fourth station milk. So Uta has chosen at least one item from every station. Now Tim has chosen fruit salad here, fish here, pie and cake both from this station, and milk and coffee from this station. So this is true until here, because second student also have chosen at least one item from every station. Now we check the third one. Yuan has chosen spaghetti and fish from second station, pie from third, and soda from fourth station, but Yuan did not select any of item from the salads. So the statement D, which is every student has chosen at least one item from every station. This is what we can write informal this statement. It is given for all student S and for all station Z there is an item I in Z such that S chooses I. It means that every student have chosen at least one item from every station. So this is false because UN has not selected an item from the first station salads. So this statement is false. Its informal version can be written as every student choose at least one item from every station. This statement is false because UN did not choose a salad. So this is how we can interpret and the multiply-quantified statements, and we can write the formal statements into the informal version. So in such situations these multiply-quantified statements occur, and we now discuss how to another example of how to write multiple quantified statements informally. Then we shall discuss an example in which we shall discuss how to convert informal statement into a formal statement. In this example we have the part A is for all positive numbers X. This statement is something different. It involves purely the mathematics, but in the previous example we have some common problem in the daily life. In this example we have for all positive numbers X there is a positive number Y such that Y is less than X. What does it mean? Means for all positive numbers X there is a positive number Y such that Y is less than X. Means there is a number which is less than, there is a positive number which is less than every positive number. This is informal version of the statement given in part A. There is a positive number Y which is less than every positive number X. This is we can write it as, but we can write it also as given any positive number there is another positive number that is smaller than the given number. So given any positive number, there is another positive number that is smaller than the given number, means for all positive numbers. So this is the informal version of the statement given in the part A. Now in part B, we have there is a positive number x such that for all positive numbers y is less than x. How to write this statement in an informal version? It means there is a positive number, it could be any positive number, such that for all positive numbers y is less than x. Means there is a positive number with the property that all positive numbers are smaller than this number. So this is how we can write the statement in B in the informal version. Now we consider an example in which we shall write some informal statements into by using multiple quantifiers for all and there exist. For example, in the part A here in this example, we have everybody loves somebody. Here we have everybody will be used in the sense of universal quantifier statements, that is for all, and somebody here will be used as there exist or existential quantifier. So how to translate this statement into a formal statement in logic? Everybody, as I have told you, everybody will be used in the sense of universal quantifiers. So we use for all people x. So this will express, or this will give us the translation to this everybody. Now somebody will be used as there exist or existential quantifiers. There is a person y such that x y what loves. So we can write it as x loves y. Here we have expressed x as a everybody for all people x, and y as a somebody. Here there is a person y. So this is how we can translate this informal statement into a formal statement. If we change the order of everybody and somebody in the part A of this example, means somebody loves everybody, then the placement of quantifiers will be changed. Here for somebody we'll use there is a person x such that for all people y, for all people it comes now at the end, comma x loves y. Now here x is basically there is a person, which means somebody, y means everybody, x loves y means somebody loves everybody. This is how we translate into formal language. Now in the part C, any even integer equals twice some other integer. So this is very famous, that is any even integer can be written in the form of 2n where n belongs to z. We have discussed such statement in the basic number theory when we have discussed number theory. So how to translate this statement, this informal statement, into formal statement? Any even number. Here everybody or any means for all, every. So wherever you see any or everybody or all, these will become we will use universal quantifiers instead of such type of words, and wherever you see somebody, there is, or some, such type of words will be translated by using there exist. So if we have any here, it means for all even integers equals twice some other integer. Now here we have some means there exist, and any means every, for all. So C can be translated as into formal language. For all even integers m are the even integers, there exists integer n, some integer such that n is twice of this. So here I think I reversed it. It should be like this. It should be m is equal to 2n, where n belongs to z. So don't see this. The correct statement is this: m is equal to 2n. For all even integers m, there is some integer n such that m can be written as twice some integer n. So this is how we can translate the statement, informal statement C, into a formal statement. Now in part D, there is a program that gives the correct answer to every question that is posed to it. Now here we have there is, so it will be used as existential quantifier. Here we have every question, so this will be used as a universal quantifier, universal statement. So this statement is basically will be translated like this: there is a program P is any program, there is a program P such that for all questions, here we have universal quantifier, here we have existential quantifier, such that for all questions it gives correct answer. So this is the formal version of the statement in D. So this is how we can use quantifiers to write multiple quantified statements, and we can translate informal and formal statements. Now, the negation of multiple statements. How to negate a multiple quantified statement? The negation of, if we are given a statement like this, in which we have first we have universal quantifier for all x, and then existential quantifier there exists y, such that p of xy is some predicate. So how to negate it? To negate it, we shall negate this. For all will be converted to there exist. There exist will be converted to for all, and we shall apply also negation on the predicate not p of xy. Here please take care about when we write for all x, we write comma after for all x, and such that after there exist. So when this for all will be changed as there exist into existential quantifier, we shall write such that after it, and then this there exist will be changed as for all into universal quantifier, and after universal quantifier we use always comma. So take care about such that and comma also, where we have to write such that and where we have to write the comma, and then we negate the predicate also here, not p of xy. So this is how we negate the multiple quantified statements. A similar sequence of reasoning can be used to derive the following. In this case we have first for all and then there exist. If we are given there exist and then for all, there exists x such that for all y q of xy. If we apply the negation on this, that is, if we take the negation of this statement, when we apply the negation, there exist will be converted to for all, such that will be converted to comma, for all y means for all will be converted to there exist y, and this comma will be converted to such that, as we have discussed in the uppercase, and we shall apply then further finally the negation on the predicate not q of xy. So this is how we can negate the multiple quantified statements. For example, if here in this example we shall negate the multiple quantified statements. For example, in part A we are given for all integers n, there is an integer k such that n is equal to 2k. So how to negate it? This for all will be converted to there exists integer n, or there is an integer n. This comma will be converted to such that, and there is an integer will be converted to for all integers k, such that will be converted to comma, n is equal to 2k, we shall apply the negation on this also. Negation on this will give us n is not equal to 2k. Here we have n is equal to 2k. What is the negation of this? The negation of this is n is not equal to 2k. So this is how we can obtain the negation in multiple quantified statements. Another example, this. Here we have existential quantifier. There is a person x such that for all people y, comma, x loves y. So how to negate it? We negate there exists into universal for all people x such that will be converted to comma, for all people y will be converted to there is a person y, comma will be converted to such that x loves y. What is the negation of this x loves y? X doesn't love y. So we have the negation of this statement given in B as this. This is how we can write the negation of multiple quantified statements. Next is the nested quantifiers. Two quantifiers are said to be nested if one is within the scope of the other. That is, we apply the first such that on the other. For example, here we have for all x there is y such that here x y is such that x, we apply x such that y is also true. Or you can say that for example, for all x there is y such that this is the same thing as for all x q of x, where q of x is there is y p such that p of xy, means one is in the other. Here we have for all x q of x such that q of x is there is y such that p of xy. So this is one is within the scope of the other. This is basically the nested quantifiers. To understand these statements involving many quantifiers, we need the quantifiers and predicates that appear. So we consider an example here. Translate into English this statement. You can take it like this also, this, because one is within the scope of other, where the domain for both variable consists of all real numbers, means x belongs to R and y belongs to R. This statement says that for every real number x and for every real number y, if x is greater than 0 and y is less than 0, then the product of x and y is less than 0. That is, this statement says that for real numbers x and y, this can be stated more simplistically, you can say that this like this: the product of a positive real number and a negative real number is always a negative real number. You can write it as also for all x, this, comma, you can write, or for all y, we have x greater than 0 and y less than 0, implies x dot y is less than 0. What does it mean? It means the product of every positive real number and a negative real number is always a negative real number. Another example to this is write the following statements in English using the predicates s of xy, say that s of xy is x shops in y, where x represents people and y represents stores. For all y, s John y. Now John is within the scope of y, where the domain for John is. Now how to write this statement informally? For all y, s of John y means John is a particular person. John shops in y means in every y, in every store. John shops in every store, because here we have y, here we have John. If we replace it here, x will replace John, y is replaced by y also. John shops in y, here we have every, so means or all, most. So how to write the statement into informal language? We can write it as John shops in every store. The other statement is this: there is x for all y s of xy. What does it mean? Somebody, there is x. Here we have there is x, means there is a person. For all y, all the stores, means x, somebody shops in every store, because here for x we have there exist, means there is somebody. For y we have all or everybody. So there is a person. How to translate it? There is a person who shops in every store. So this is how we can translate this statement, which is basically the nested quantification, which we have discussed here. Now a table which will clear us what is a truth value of multiple quantified statements when they are true and when they are false. Table for quantification of two variables. If the statement is like this: for all x, for all y, p of xy, it is true when p of xy is true for every x and y, means every x and every y. So because p of x is some predicate and x is here for all and y is here for all, this p must be true for all x and for all y. So this statement will be true when p of xy, predicate p of xy, is true for all x and for all y, or you can say for every pair of xy. And when this statement will be false, if we can find some pair x and y for which this predicate p of xy is false. So when this then this predicate will be false if at least one pair we can find for which p of xy is false. Now similarly, this statement is for all y, for all x. We have just interchanged the place of x and y. This will remain true in the same case and remain false for the same case. Now this statement, for all x there is y, p of xy, when this statement will be true, this statement must be true for every x and for at least one y, because for x we have for all and for y we have there is some y, for at least one y. So this statement must be true for every x there is a y for which p of x is true, means for all x, if we choose x one by one, and there must be some y, at least one y, for which p of x is true. Then this statement will be true. And when this statement will be false, there is an x such that p of x y is false for every y. We reverse this statement, or we take the negation of this statement. There exists x such that for all y, p of not p of x, we take the negation as this statement will be false when this is true. Or you can write it as this: there is an x such that not p of x is true, or p of x is false for every y. And this statement, there is an x such that for all y, p of xy, this statement will be true when there is an x for which p of xy is true for every y, and this statement will be false in this case. For every x there is some y for which p of x is false. So now these statements, when these statements will be true and false, both of these statements will be true when there is some pair xy for which p of xy is true, and this statement will be false when for p of xy is false for every x and y, for every pair x and y. So this is basically summary of the multiple quantified statements which involve only two quantifiers, either for all or there exist. Then we can check the truth value of such type of statements like this. Now we take an example to further understand this this concept. Write the following statement in English using predicates: c of x where C of x is a computer science major, T of xy, where T of xy is x is taking y, where x represents students and y represents courses, and we have to tell whether this statement is false or not, or we have to find it's in informal language. So we have for all y there is x, not C of x and T of xy. For all y means what is the domain of y represents courses and x represents students. Means for all y means every course, there is some x means there is some student, so that x is not a computer science major, because C of x is, if C of x is a computer science major, then not C of x is not a computer science major, and T of x is y is x is taking y. So how to write this statement informally? In every course there is a student. There is a student y, means there is a student who is not a computer science major. So this is how we can, here we have for all y means in every course there is some x, there is some student, there is a student who is not a computer science major. If he is not a computer science major, then he's x is not taking y. So this is understood. So we can write it in formal way like this. The statement, for example, this is the statement, this says that for every course y there is a student x such that x is not a computer science major and x is taking y. Here we should add here x is who is not a computer science major and x is taking y. In every course there is a student, yes, who is not a computer science major, means he is not taking, and he is, in every course there is a student who is not a computer science major. In every course means in every course there is some student. What does it mean? It means that student is taking that course. What this means, that in every course means हर कोर्स में कोई ना कोई एक स्टूडेंट है, means वो स्टूडेंट जो है वो कोर्स ले रहा है, but he is not a computer science major. So this is I think this is the correct translation of this statement. Now we shall discuss what is the relation among for all, there exist, and or. If q of x is a predicate and the domain D of x is the set x, x2, x3 and so on xn, then the statements for all x belongs to D, q of x, and q of x1 we write the conjunction here, q of x2 conjunction and so on conjunction q of xn. Both of these two expressions are equivalent, are logically equivalent. For example, let q of x be x and x is equal to x, and suppose D is 0, 1, the for all x belongs to D, q of x can be written as for all boundary digits x and x is equal to x. This is equivalent to saying 0 and 0 is equal to 0. Obviously the conjunction of 0 and 0 is 0 and conjunction of 1 and 1 is 1. So whether we write like this, for all x belongs to D, which is 0, 1, x belongs to D, we have x and x is equal to x. Whether we write this or we write 0 and 0 is equal to 0 and 1 and 1 is equal to 1. So both these two statements are equivalent. So we can write instead of conjunction between multiple statements, we can write them in short like this by using universal quantifiers. Similarly, if q of x is a predicate and the domain D of x is the set x1, x2, so on xn, then the statements there exist x belongs to D such that q of x and q of x1 or q of x2 or so on q of xn are logically equivalent. This statement means that for some x, q of x is true, means there exists some x belongs to D in the domain such that q of x is true. Or we can write that this statement, this whole statement will be true if at least one of q of x1, q of x2, q of xn is true. So logically these two statements are equivalent. For example, we have let q of x be x or x is equal to x, and suppose D is 0, 1, the same example, and the x belongs to D. Q of x can be written as for all binary digits x or x is equal to x. This is equivalent to saying 0 or 0 is 0, 1 or 1 is 1. So there is a relation between disjunction operator and the existential quantifier. So we can relate these operators: existential, universal, quantifier, conjunction and disjunction. The next is rules of instantiation. The rule says if some property is true for everything in a domain, then it is true for any particular thing in the domain. If I say that in a class of computer science, of discrete mathematics, all the students are older than 20 years, if I say this, आपकी क्लास में, डिस्क्रीट मैथमेटिक्स की क्लास में हर बच्चा जो है वो 20 साल की उम्र से उसकी उम्र ज़्यादा है, तो फिर अगर ये स्टेटमेंट मैं दे देता हूँ, ठीक है, तो दिस स्टेटमेंट इज़ ट्रू फॉर एवरी स्टूडेंट, दैट इज़ कोई एक पर्टिकुलर, फॉर एग्जांपल कोई स्टूडेंट पढ़ता है क्लास में, फॉर एग्जांपल आमिर, तो मैं पूछता हूँ जैसे कि आमिर की एज क्या है, तो डेफिनेटली आमिर की एज 20 से ऊपर ही होगी. तो मीन्स इफ ए प्रॉपर्टी होल्ड्स, if a property is true for everything in a domain, then it is true for any particular thing in that domain. For example, all human beings are mortal, means सब इंसानों को मरना है, they will be dead. Socrates जिसे आप सुकरात कहते हैं, Socrates is a human being, means Socrates is a mortal, और सुकरात मर जाएगा. Therefore this property will hold for Socrates also. So this is basically the rules of instantiation. Now we can apply this rule in mathematics and in computer science also. For example, in mathematics we have an example. Suppose you are doing a problem that requires you simplify r power k plus 1 into r, where r is a particular real number and k is particular integer. For basic algebra we know that for all x belongs to r, mn belongs to z, x power m, this is multiplication here, x power m into x power n is equal to x power m plus n. So this is a rule. Another rule is x, for all x belongs to r, x power 1 is x. We can use these two universal statements which are true for every real number. We can use these two universal statements to simplify this expression, where r power k plus 1 into r is basically what r. We can use by using this rule we can write r is equal to r power m, and then by using this rule we can add up these two powers of r. This is k plus 2. So in simplifying this expression we have used these two universal rules, which are you can say universal properties which are true for every real number, to simplify this expression. Now what is the universal modus ponens? We have already discussed what are the modus ponens and modus tollens. Here we shall study the universal modus ponens and universal modus tollens. The rule of universal instantiation can be combined with modus ponens to obtain the rule of universal modus ponens. This is the formal version of this universal modus ponens, means for all x, p of x is true, q of x is true, then this whole statement is true. Here we have a particular value of x which is a, means x, if we put if this statement is true and p of a is true, where x is basically a. We give a particular value to x. If p of a is true, then q of a must be true, because this universal statement is true. If a particular case of this statement is true for a, then the particular case of for q of x is also true. This is basically the universal modus ponens. An informal version of this universal modus ponens is, if x makes p of x true, then x makes q of x true. A makes p of x true, a makes q of x true. So this is the informal version. For example, if a number is even, then its scale is even. So this is basically a universal statement. You can say that for all x, e of x implies s of x. This is universal conditional statement. This is true. And we say that e of k is true. That is, if a number is even, then its scale is even. This will translated like this: k is a particular number that is even. If k is a particular number that is even, then its scale must be even. Scale of k is even. So this is basically the universal modus ponens. Similarly, we can define universal modus tollens. You know the simple modus tollens. We generalize here this statement, universal conditional statement. If for all x, p of x is true, implies q of x is true. If not q of a is true, for some particular value of x is equal to a, if not q of x is true, means q of a is false, then p of a must be false. So this is universal modus tollens. An example of this: all human beings are mortal. सब इंसान जो हैं वो क्या है, mortal हैं. Zeus is a human being. अब Zeus जो है वो human being है, therefore Zeus is mortal. This is universal modus ponens. But if we write it like this: h of x, x is a human; m of x, x is mortal; and let z stands for Zeus, the argument becomes, for all x, if h of x, then m of x, not m of z. Means, what is m of z? This, not m of z. Z is not mortal, because if m of x is given as x is mortal, then not m of x is, what is this? X is not mortal. If here z is not mortal, means Zeus is not mortal, then we can draw a conclusion by using modus tollens that Zeus is not a human being. So this is valid by universal modus tollens. Next, what is the converse error in the universal modus ponens? We have discussed also the converse error in the modus ponens and modus tollens. Here the converse error is basically in the universal modus ponens. If we are given for all x, if p of x, then q of x, and q of x, q of a for some particular value of x, which is a, if q of a is true, p of a is true. This is the converse error, because we have to place this here and this here, or you should take the converse of this statement, as we have discussed in modus, the converse error of modus ponens. This must be, q of x must be here and p of x must be here. An example of this: all healthy people eat an apple a day. Alan eats an apple a day. So we cannot draw a conclusion Alan is a healthy person. This is basically the converse error in the universal modus ponens. Inverse error will be same like in the inverse error as we have discussed in the modus tollens. His statement is, for all x, if p of x, then q of x, and we say that not p of a is true, then not q of a must be true. So this is basically the inverse error. It should be we should have take the inverse here of this universal conditional statement. If we take the inverse of this statement, this becomes the universal modus ponens, I think. Then this statement will be true. All healthy people eat an apple a day. Smith is not an healthy person. We cannot conclude here that Smith doesn't eat an apple a day. So such type of errors basically we have discussed in the previous lectures when we have discussed modus ponens and modus tollens. Here they are in the form of universal statements. So for today it's I think enough, and we have discussed today statements containing for all and there exist, means universal and existential quantifiers. We have discussed nested quantifiers and the relation between for all, there exist, conjunction and disjunction. We have discussed universal instantiation statement, universal modus ponens, tollens, and the converse and inverse error for the modus ponens and tollens. So we stop it here. Until the next lecture, Allah Hafiz.